بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is the second lecture in the course CS316 about Introduction to AI and Data Science. And today I'm going to provide you an overview about what is artificial intelligence, machine learning, and deep learning, and the different type of learning models. So let's get started. We already covered this slide yesterday. This is just a refresher. So as we already mentioned, artificial intelligence is the general umbrella which started in the early 50s in this century, 1950s. And basically the AI at that time was just to mimic the human intelligence by trying to incorporating like different type of rules that we can develop them as a program using programming. We develop these rules in order to infer some kind of intelligence and decision making. It was applied, for example, in different type of games like chess, for example, and also different type of search algorithm have emerged from the artificial intelligence community in the early days. So when the problem becomes complicated, and as we already introduced, sometimes you are not able to infer all the different type of rules that are able to transform the data into output, especially when we have very complex patterns and very complex rules. And this is where machine learning comes into play, is that instead of programming the rules, we try to infer the rules from the data, from the input, okay? So machine learning, there are different types like supervised and unsupervised. And one of the early applications of machine learning is try to detect spam algorithms, for example, and do different type of classifications, clustering, for example, understanding the customer behavior based on some features. And with the evolution of machine learning and also neural networks, and especially when the computing capabilities becomes bigger and bigger, both in terms of processing and also in terms of storage, neural networks have arisen as an alternative to traditional approach, and we start talking about deep learning or deep neural networks. So basically, deep learning is pretty much related to the use of neural network, but with deep layers, okay, with a lot of neurons. So neural network is an old technology, I mean, from the 80s. But it was not popular too much because it is very computation intensive. And at that time, the computing resources were very small and poor. So they cannot cope with the requirement of very large and deep neural network models. This is why neural network, from conceptual perspective, it existed a long time ago, but from practical perspective, it's only from 2011, 2012, with the emergence of graphical processing unit, what we know as GPUs. So the processing of very heavy networks like neural network becomes possible, and then it has almost replaced all the different classical techniques because it allows to extract the features automatically instead of manually, and it can extract the features intrinsically by processing the data and try to identify patterns instead of statically identify patterns manually. So what is the difference between machine learning and the traditional programming approach? As already introduced, in early days of artificial intelligence, it was possible to infer the different type of rules that can transform data into output. So all the work was just to program these rules, like expert system are one of the early AI systems that contains rule-based approach. And when you provide certain type of input, it will apply these rules in order to make a particular type of decision. So that was possible in the early day system, but as the data becomes huge, more complex, more difficult to find patterns, we don't only rely on textual data, now we can rely on sequential data like audio files, video files, pictures, images, any kind of data sources. So this traditional approach becomes very, very difficult. You can easily, for example, if you know the rules, how to calculate, for example, the profit, the margin, how to calculate the average, the mean, you can implement these rules using traditional approach. But for example, if you have a picture and you'd like to find what is inside this picture out of the pixel colors, that becomes more difficult. Okay, if you have a text and from the text you want to say whether this text has a positive sentiment or a negative sentiment or a neutral sentiment, it's not possible to find a rule-based approach that will capture all the different type of circumstances and conditions in this particular type of application. And this is why machine learning comes here. So instead of developing the program, we're going to infer the program. We infer it from what? We infer it from the input data and the output data, the outcomes. Of course, if we have the outcomes or the output data, this is what we call supervised. And sometimes we have just raw data and we would like to identify patterns. We don't know what kind of patterns, but there are some type of relationship where some algorithms are able to find the relationship between these data using machine learning techniques. Okay. So machine learning comes in to different versions. We have supervised learning. And in this particular case, we use labeled data. So we have data and the corresponding outputs. And then we can train models in order to make, for example, prediction or regression or make classification. For example, in the case of we have numerical data, we can develop models to predict housing prices based on the attribute of a house. For example, if you know the attribute of the house in terms of the surface, the number of rooms, and different type of features, and its location, we can have an estimate, a good estimate, not the exact price, but a good estimate of what could be the housing price based on different information that we collected and used to build a predictive model. We can do also medical image classification. Imagine that we have an X-ray picture or we have a CT scan picture and we want to make a diagnosis in healthcare, whether the patient is sick or has normal conditions. Okay, for example, we can use this in COVID-19, for example. A lot of research have been done to detect whether an X-ray has a COVID-19 symptoms or doesn't have a COVID-19 symptoms. So unsupervised learning, we don't have labeled data, so the data is completely unlabeled. And this is used basically in clustering. For example, we can have a lot of customers and you'd like to make a classification of this or clustering of these customers. Customers that, for example, are likely to purchase more products, or others, for example, that they are less likely based on their features. We can make market basket analysis. We can do different type of analysis, and we're going to talk about these different type of examples. We have semi-supervised learning, and here, in real world, usually we don't, when you want, for example, to have million of data that is labeled. Imagine that you have pictures and you want to train a supervised learning model, but you need to label 1 million picture in order to get an accurate model. This is usually very difficult. Okay, it requires a lot of human resources and a lot of also financial resources. Like, for example, for training ChatGPT, the instructed model, they needed human power in order to label. So there was more than 4,000, I think, human labor that cost a couple of $millions to create a data set that is labeled for the supervised fine-tuning of the large language models. So in semi-supervised learning, usually we use subset of the data that is labeled to create an initial model, and this initial model will be used to also label additional data that is completely unlabeled, instead of having everything manual by humans. And reinforcement learning, so this approach is based on a reward function. For example, it's trial and error. We're going to teach an agent to take appropriate action inside its environment. I'm going to introduce all this with illustrative examples, but just to give you some intuitions about this. Like, for example, we can teach, for example, a self-driving car to drive safely into a particular environment. Okay, so it will use trial and errors, and whenever there is an error, we give a negative reward. When there is a good action or correct action, we're going to give a positive reward. Okay, so these are the different types of supervised and unsupervised learning, and also we have reinforcement learning. So we usually can have classification problems or regression problems. The only difference is the type of the output. If the output is a numerical value, like for example the price. The price can be a float number. We cannot classify because usually with classification we have a finite number of classes. This is why I call it classification. I have 3 classes. I want to classify a picture as a dog, cat, or bird. So the number of classes is known, is an integer. However, if the number of classes is continuous, so we talk about regression. Clustering, this is unsupervised, so we have data completely unlabeled, and you want to identify clusters. And the clustering algorithms, they can give different type of outputs depending on their parameters, depending on several parameters. And reinforcement learning, as already explained. So let's take a few examples of supervised learning. So the first example is to automatically classify emails. So as either going to the inbox or going to the spam filter. So how this actually happen? We are going first to identify features of every email. Now usually if you open your email, you can identify some keywords, maybe in the subject or inside the body, that will give you some kind of likelihood that this email could be a spam. Like for example, what? You have won, I don't know, $100 million, or you are the winner of a big award, something that you don't even know who is the sender. So of course, usually we can train machine learning classifiers, okay, so that they can learn based on the words and the features. Like for example, we can collect the features from the body of the text, from the metadata, from where this email is coming. Even some senders, for example, we can blacklist them. So we can have a collection of senders that are blacklisted, they know they are spammer. We can also identify some particular keywords that can trigger a flag that this is probably a spam. Okay, so machine learning models were trained as classifiers, like for example, the naive Bayes, the support vector machine, to predict if an email is spam based on features like the content or the sender information in the metadata. And at the end, this helps to reduce a lot. So in the early days of email, I remember when the email was introduced in the early 2000, you receive everything into your inbox, a lot of spam. And now we don't almost receive anything. And because the good thing is that these spam filters, they learn over time. Whenever there is a new email that comes as a junk, it's going to go inside the machine learning model, and the machine learning model will be updated. And in your email, sometimes you have also the option to press whether an email is spam or not. If you press this is a spam, this is going to be tagged. It will go to the engineers. They were going to incorporate this into the learning model, and it keeps learning, until at the end we reach almost 100% accuracy of the spam filters. It's really very, very scarce that we find spam into the inbox or some legitimate email, it goes into the spam filter. Okay, not like in the early days. Okay, some of the email, they go to the junk because they are misclassified. So we try to reduce the misclassification of the email. So the unsupervised learning, so and the most important approach is the clustering. So here the objective is, for example, to group customers into distinct segments based on their behavior and characteristics and features. But the problem, we don't know what are the different clusters, because we only have information about the customers. We have, for example, their names, their expenditure, their location, maybe their financial state. So applying clustering algorithms to segment the customer based into distinct group, and the outcome is to identify the target audience clusters to optimize product marketing and sales strategies. So how this is useful? Why this is useful? Because people, when they do marketing, they will spend money. So imagine that they will spend money on everyone, but there are some group of people that are less interested than the others. So they try to find the interest of people with respect to some product. So in this case, they can have a directed marketing strategy that will optimize the cost and maximize the benefits. Okay, but of course, they will need to run some clustering algorithm to make identification. For example, grouping people by age, certain type of product, they are better for youth, some other for older people, and based on this, they can make targeted marketing campaign. And you can see now in social media, if you want a marketing campaign in social media, you have the ability to choose the ethnicity, the group age, the gender, and different type of attributes. Okay, so instead of doing this completely randomly, it's better to leverage the data that you have, to understand your data, make predictive models using clustering, and then you can lower your marketing cost and increase your incomes and benefits. Yes?
So in this type of learning, there is no labels, right?
Yeah, there is no label, so it will be discovered. And this is why clustering algorithms, they can give different type of clusters.
So if, in theory, if we don't tell a model that this type of customer likes this type of product, then how does the model learn this?
So yeah, this depends on depending on the algorithm. There are some hyperparameters, like for example, k-means. You can specify how many clusters you want to identify. Okay, for example, I want to identify 3 clusters, 4 clusters, and based on this, you can understand what are the characteristics of the cluster, and based on these, you can take informed decisions. But you don't have any clue about what this cluster is gonna, how this cluster will be formed. But you will have a logical relationship between all the members of this cluster, because it will try to minimize a certain error with respect with the objective that you want to achieve. Okay, so at the end, you will be sure that these clusters contain a group of members that are related with each other with respect to a specific objective. So you know your objective, have your data set, but you don't have any clue on how to make the segmentation or the clustering. Yes?
So is neural network a subset of supervised learning or applies unsupervised learning?
So neural network is it can be used it's basically used in supervised learning, in semi-supervised learning, in self-supervised learning, and also it can be used in unsupervised learning. Yeah, it can be used in any kind of technique.
So it does not need a label data or something?
Yes. Neural network, basically, it cannot be unsupervised because it's based on backpropagation. So backpropagation, you need to know the ground truth to be able to provide a feedback. So it's, in the worst case, it is either self-supervised, we're going to introduce this, semi-supervised. Okay, but there are other algorithms that they don't require, so you define your objective without needing to have the ground truth. The neural network will require the ground truth in order to make the error between the expected output and the correct output. Okay, so it's mostly for supervised learning. So semi-supervised learning, and in several situations in real world, you don't have the luxury of labeling millions or trillions of data. And sometimes you don't find even a data set. So in this case, you can start from a partially labeled data, and this data will be used to train a model. So you're going to have an initial model, not perfect, but still it's able to make some good prediction to some extent. So what's the idea here? We can take the unlabeled data and try to label it using the trained model. Okay? Let's assume that we will have 70% of correct labels. We're going to take these 70% of correct labels, adding them to our original labeled data set, and train again. So we're going to have better accuracy. Okay? And we can repeat this process a couple of times, and this will save to some extent, okay, the need for labeling a huge amount of data. So once the model is able to learn initial features, it's able to make good prediction, not to 99%, but let's say 70%. So over 1,000 images, I can take 700 and incorporate them into my data set and retrain again to improve the accuracy. Because the rule of thumb, usually, the larger the data, the highest the accuracy. Okay? And whenever it's impossible, for example, here we can have just partial amount of data, so we can learn a little bit the pattern of an orange, the pattern of a banana, and then we can take the unlabeled data and train again the machine learning model in order to predict with higher accuracy. So this is okay. This is an example here. So initially, we're going to apply supervised learning. Let's assume that we can train a small sample of images, let's say 100 images, to recognize basic fruit features. And based on this, we can take, after we train this initial model, we can take 1,000 unlabeled images and predict them using our initial model. And if we have, for example, 700 correct classification, we consider this as pseudo-labeled images. And we take the 100 images with the 700 images, put everything together, and train again. We're going to have a better accuracy. The new model can be also used to train the additional data that is unlabeled, and reiterate a couple of times until we can get a good accuracy. Yes.
How do you identify the number of correct labels? How do you get the number 700?
There is no rule of thumb. I mean, usually you try to label as much as possible, okay, depending on the cost, depending on the time, depending on many constraints, depending on the availability of the data. Sometimes the data is not really available.
After receiving the data, how do you know the number of correct labels out of the ones we give?
Yeah, you can visually track them, you know. You can visually track them. I mean, tracking them is easier than labeling. Labeling is usually a tough task. But now, with the emergence of generative AI and large language model, there are tools that are able to do labeling automatically, you know. Yeah. Other questions? Okay, self-supervised learning. Now, let's talk about self-supervised learning. We talked about supervised learning. We're going to require a huge amount of data to make supervision. Unsupervised, we don't have labeled data. Semi-supervised, we have a small amount of labeled data and a huge amount of unlabeled data. And semi-supervised here is completely unlabeled, but is going to learn from itself. And this is how large language models, for example, were trained. So usually in large language models, we're going to first pre-train a model just to learn the language. What does it mean pre-train the model? We're going to create what we call a pretext task, okay, that will try to generate labels from the data itself. So in the case of text-based large language models, usually we try to predict the next token. So what we will do, let's imagine that we have a huge amount of text that we collected from Wikipedia, from the internet, and so on. So we're going to take a sentence, and then we're going to train the model. If I give you a certain context, this is the next word. And with several iterations, is going to learn, given a certain sentence, how to complete this sentence. This is what we call text generation or text completion. So it's like a model is going to learn a language. Just knowing the language, it's able to generate what is the most likely word that will come after a certain context, contextual information. Okay? Yeah. In the context of an image, we can, for example, use self-supervised learning to do image unpainting. You know, some images are distorted. They have distortions. And in one of the tasks, for example, I would like to recover a distorted image to a good quality image. So I can, for example, take a good quality image, distort some of the parts, and then train the model to recover, okay, the distorted part. So this is another example of self-supervised learning. Is going to learn from itself in order to label the data. Okay, and this is basically the essence of what we know as generative AI. Most of the generative AI now, they are self-supervised learning. Of course, they could be also supervised, but now, for example, GPT is basically a self-supervised. It's using the same strategy that we explained over here. And now with this kind of, for example, pretext task, we can have a model that is able to understand the language or languages, because usually we teach the model on English, Arabic, or different type of other languages. So we don't need to have large labeled data set, and the data provides its own supervision through structured tasks. But usually these models are not sufficient. generating the text, I would like that the model can perform additional tasks, like for example, answering questions, like for example, writing codes, like for example, making inference, having reasoning, understanding. So in this case, we can actually augment the model by what we call fine-tuning. So fine-tuning, we're going to have a small corpus of labeled data. For example, I will provide 1,000 questions and answers. And I'm going to train the model that is pre-trained on answering questions, on summarizing tasks, on making machine translation, on doing different type of tasks, writing code. And this is how GPT is able to do all of these things. Okay, is based on fine-tuning of pre-trained models that were self-supervised. So here we use self-supervised, and here we use what? Which type of learning? Supervised. It's fully supervised because all the data will be labeled with very specific tasks. Okay? And now here we have different type of models and how we can do that. For example, GPT, it uses a context to predict the next word. The cat sat on the mat. Okay? BERT, it uses a different approach. It used masked word using the context. For example, I can give the beginning of the sentence, the end of the sentence, and the missing word. So it's going to train itself to find a missing word within a certain sentence. This is how BERT was actually developed, yes.
What is fine-tuning in this context?
Yeah, fine-tuning, it means training the model again on a labeled data so that the model is able to do additional tasks with more accuracy. Okay? Because in the beginning, training pre-trained model is even more difficult because you need a huge amount of data. You cannot label the data in the internet.
That's right.
You have trillions of words to train. If you put all the people labeling, is going to be very costly and also still time consuming. So we don't use in pre-training, we don't use supervised, we use self-supervised. So either we predict the next word, either we predict the missing word. And based on this, we can learn a language. And based on this language, we can augment the language to do مثل شخص مثلا الآن it will go to Japan to make studies. In the beginning, doesn't know the language. So he spent 1 year learning the language. So he's able to speak Japanese. After 1 year, he's going to do what? He's going to go to the university and, for example, acquire engineering skills, capabilities, and so on. This is fine-tuning. Okay? It means augmenting the pre-trained model is like learning a language to be able to speak, to understand the context, and then leveraging this knowledge in order to augment the model to do additional tasks like summarization, classification, and other type of tasks. Yeah.
So again, why do we use labeled data when we find tune? It's already self-supervised.
Yeah, now imagine that you have a pre-trained model and you want to summarize text. It's not trained to summarize text. It's trained to give you a text, will give you completion. Just continue an existing text. Didn't learn how to write code. It didn't learn how to translate a text. It only learned a sequence of words and how to complete. So this is a different type of task. So we need fine-tuning, and fine-tuning must be supervised because you will instruct, and this is why we call them instruction-based models. You're going to instruct the model to behave in a specific way in order to solve particular problems. Yeah.
Doctor, if you want to give a large label of courses as written here or tasks, as you say, can we use semi-supervised?
Yeah, it's possible, but usually fine-tuning, I mean, couple of thousands of examples is able to generalize very well on language model depending on their capabilities. Sometimes just 1,000 example, 100 example, 5,000 example, it's trial and error. It depends on the model capabilities, how it was pre-trained, on which like of corpus, how it generalizes to different type of tasks. There are many parameters that comes into play about later on how huge should be the data set. Of course, some models, they may require just small examples, and this is why we call it few shots or zero shot. Few shot, it means that the model is able to learn from 1 or 2 examples. Zero shot, it means it's able to learn from 0 examples, just it was using its pre-trained capabilities. Okay, so few shots, only small examples, it's able to learn and mimic the same examples. Yes.
The only objective of the self-supervised learning is to complete next work, or does it have other applications?
Sorry?
The objective of the self-supervised learning
Yeah.
is it only to continue the next work, or it has other applications? Let's say?
Yeah, I mean, GPT, it predicts the next word. Okay? Some other models, they can use different strategy, but usually it's basically generating the next token for LLMs. This is like what we call decoder-based architecture.
But for GPT, it is fine-tuned after it got the self-supervised.
Yes, it's after self-supervised, it's fine-tuned on supervised data set. Yeah.
So GPT can write your code from scratch. I mean,
Yeah, it was trained, all the Stack Overflow, it was used to fine-tune and also teach ChatGPT on how to do that. Okay, tutorials,
so it does not. It has nothing to do with the predicting the next word. It's just
Yeah.
generating.
Yeah, in any case, even later on, instruction file, it's always generating, but we need to instruct how to generate depending on the question or the prompt. Okay?
Is it completing the next word, or is it like extracting or something like that?
Yeah, completing the next word. It's basically everything in ChatGPT. It just try to predict what will be the next word, even writing code. But it was trained in such a consistent way that it is able always to provide you the correct output. Okay, I'm going to explain you just in a few slides with more details. So the pre-trained model is basically to find the word relationships. Okay, and this is where the law of large numbers and statistical models comes into play to get statistical convergence toward the right distribution of the patterns to be identified. Now, for example, let me tell you how BERT works. Now, if I tell you read this word, how can you read it? Yeah. حبر بس خبر خير خبز. So without a context, you can read it in different ways. Now, how BERT was trained, it was trained. Now, if I tell you what is this word, خبز, is there any doubt? No. How did you know that? Your brain was pre-trained, okay, to complete, because you have a lot of sentences that you have read before, and this makes only one possible solution here. And this is BERT, how it's going to see a lot of sentences, and then it's kind of not memorizing, but it's going to have the ability, because memorization, it means it has to see the same example to infer it correctly. No. It will have new capabilities like a brain to be able to infer any word in the middle, even if it was not seen before, even if the context is completely new. Okay, now if I take this one, khabar. This one, you see, now we try to mimic the same human learning behavior. Okay, because you have read a lot of books before, a lot of text before, now you are able to determine with a good confidence. Now, if I give the same example to a child, maybe he will be able to find 80%, 20%, didn't learn too much. So the scale of the data and the time spent to train will play an important role about the convergence and the accuracy of the predictive model. Okay, من كان بالله فليقل خيرا أو ليصمت. Now the GPT approach is a little bit different. So let's look at the large language model as a black box. It's going to take, for example, a certain context, the beginning of the sentence, and how can you complete this one? Every morning I go to the work, school. So there are a pool of possible words that will make sense. Okay? Okay, I can go to the sky. It's not likely, unless if you have a rocket or an airplane. So there are words that are more likely to be correct and other words, so it's basically a probability. ChatGPT is going to choose from a huge list of words what is the most likely one that will come after. Okay? So to the school. And this is how ChatGPT works. When you give a sentence, it's going to provide you the most likely words that will come after. And based on this, it will choose randomly. So if I choose always the highest priority word, you're going to have always a static output. It will never change. However, it's going to change not always the highest probability, maybe the second one, the third one. We can define these hyperparameters about which one to choose in order to be more creative or more conservative in the inference side. Because I can go to my office, okay, and basically the GPT or the large language model is going to have a context which is sequential data, and will generate probabilistic text completion. But of course, we need to train this engine in order the generation not to be completely random, in order to leverage all the data that we collect before in semi-supervised way in order to generate a consistent output. Okay. So let me finish now with reinforcement learning as the last type of learning today. So in reinforcement learning, we don't use data to label. We don't have data. We don't have labeled data or unlabeled data. We're going to do experiments. It's basically a trial and error. So the system model is a little bit different. And here we talk about an agent. Like, for example, in the context of autonomous cars, we have an autonomous vehicle that will act as an agent, and the agent will work inside an environment. So always in reinforcement learning, we have an agent that we want to train, and we have an environment. So we need to define the system model as what is our agent, what is our environment. And our environment will be the environment where the car is going to navigate. And it can be, for example, a picture of the street where the car is located. Of course, it's still augmented with other data like LiDAR, 3D sensors, 3D cameras, and so on. But basically, we will have a picture. And this agent that is working in the environment will need to take actions. So what action the car is going to take in order to drive? So pushing back the gas or rotating left and right. So we will do the experiment into a simulated environment, and then the vehicle is going to drive. And whenever it does any mistake, we're going to make a negative reward. So it will try the operation again. It will learn from the negative reward, I should not take this action. Of course, there is an optimum. We will use a neural network to train a policy, and the neural network will learn about the errors. So the data is going to come from the experiment, and it will be automatically labeled whether this is wrong, okay, classified as wrong or correct, true or false. So it's like a binary classification, and based on the outcome, of course, what could be, for example, a mistake? It will crash against a wall. It will crash against a pedestrian. Okay, so we'll take this information, we update the policy in order not to do the same error. Yes?
So is there a level of rewarding? Like maybe if the same action have two different possible outcomes. Like if a car stops the middle of the road, can I go around it or wait for this car?
I didn't understand your question.
The two actions have the same reward. يقدر يروح يركب السيارة ويقدر يوقف السيارة.
نعم.
اختار.
هو is going initially it will start with random actions. شفت الاتاري games؟ Atari games مثلا شخص doesn't know how to play. He's going to take random actions. It will fail first time. Second time, okay, no, I should not do the same thing. So over the iteration, is going to learn and train. Same thing now, we're going to run a random action. I'm completely new to driving, so the agent is completely new to driving, is going to take wrong action. It will crash to an obstacle, to a wall, to different things. And based on this, we're going to update a neural network so that it will not do the same mistake the next time. Okay? Yeah.
I want to tell, but can you use pre-tested actions? For example, it doesn't have to start from the beginning where the car goes.
Yeah, of course, implementation was. There are different ways on how to send these actions. Okay, it can be random or, for example. But usually it must explore the whole state. Okay, because this action, okay, you will have a list of actions that you can take. Okay, so you make an observation from the environment. Based on this scene, I have, for example, trees, I have a driving area and so on. Based on this, what is the appropriate action? And of course, it's going to be taught on a large number of scenes. Okay, usually they record videos, real videos of driving, and then they use these videos in order to train the model to take appropriate actions. And we have the reward here, which could be positive and negative, and this is pretty much related to the policy that will learn, which will map the actions to the rewards. Okay, let me show you this example about, for example, training a model for a car to learn how to automatically park using artificial intelligence. So look, the car in the beginning is going to take completely random actions. Wandering, in the grass, in the lawn, crashing against obstacles, This is completely now, it's still learning. And we do this in simulation. We cannot have the luxury to take a car into the city and just crash over different people, So we do this one here, and usually we can also take very realistic pictures, because if you train a model in simulation and take it to the real world, it's not the same type of environment. Okay, there are different ways on how to make domain adaptation or to take real world data in order to train different models based on this. So this is going to repeat for several attempts. How many attempts? It can be thousands, millions of attempts. Okay, until the car at the end trying. Okay, look, after several attempts, it will have more likelihood for the success as compared to the initial attempts. And if we look at the video, wherever the car is, it will be able to park correctly. Okay, so it will generalize to different type of situations. Yes.
Does it need to start every time from the scratch? Or do you have already what is that? Can this model start from below?
Yeah, now this depends on whether you have a specific model or you want to have a generalized model. Okay, it depends on the objective of the study. People usually may start from scratch depending on the objective that they want to achieve. You can use also transfer learning. You take a pre-trained model and you try to adapt it. Maybe this can have a better convergence, especially if you take it from a self-driving context to another self-driving context. So instead of starting from scratch, you can leverage the existing. Yeah.